Hello everyone, hope you are doing well. Welcome to the online platform Civil Technobricks. Guys, here we will tune for the instantaneous decoding of conceptual knowledge in the field of civil engineering where study elaborates decoding the earth to build a better world. Today we will go through the core concepts of fundamentals of hydrogeology, groundwater and water table aquifers. Hydrogeology studies the occurrence, movement, and storage of groundwater beneath the Earth's surface, as shown in the diagram. Groundwater exists within the pore spaces and fractures of rocks and soil formations. The movement of groundwater follows hydraulic gradients and geological structures. Here, the water tables and aquifers are the fundamental components controlling subsurface water availability. So, with reference to the civil engineering, hydrogeology is important for foundation design, groundwater management, dams, tunnels, and water supply projects. With reference to the digital elevation model, or digital surface model, or digital terrain model, we can study the fundamentals of hydrogeology on the surface of Earth or below to the Earth's surface effectively. The interaction of Earth and water, that is the solid Earth and the hydrosphere. So the solid Earth is a combination of lithosphere, stratigraphy and rock mechanics, whereas the hydrosphere which consists of fluid dynamics and atmospheric interaction. So the hydrogeology which is the combination of the soil, that is earth, and the water. So hydrogeology links the lithosphere, that is the area which study with reference to the rocks, and hydrosphere, that is the area with reference to the study of water. So geological formations control groundwater storage and movement. Rock properties such as porosity and permeability which influence the water flow and the availability of water beneath the earth's surface. Here we can also use the geological subsurface exploration to study the properties of rock and soil for the same. Atmospheric processes such as rainfall provide groundwater recharge. Hydrogeological studies helps engineer to evaluate availability of water and subsurface conditions of the earth's surface. So hydrogeology investigates the interaction between the solid earth and the hydrosphere. Rather than the viewing water in isolation, it studies how geological structures contain direct and are physically altered by subterranean fluids or the underground water or any other fluid material. The hidden hydrological cycle. So the hydrological cycle, which consists of n number of components for infiltration, percolation and subsurface flow, they are also listed in the below. Infiltration, where surface water entering the soil matrix. Percolation is nothing but downward flow of water with reference to the gravity driven movement through the rock strata or with reference to the rock layers. And subsurface flow, which is the lateral movement, vertical or horizontal movement, we can say that, contained by geological boundaries. Now, while surface runoff is visible, or if the heavy rainfall will occur, then the surface runoff is visible, then the vast majority of unfrozen fresh water resides below ground following a complex structural journey that is called as a groundwater, or we can say that the hidden water cycle. So the most freshwater resources are stored underground rather than on the surface. So underground are the perch aquifers or confined aquifer or unconfined aquifer, or the water droplets or moisture present within the rock layers or soil layers. Infiltration is the process by which water enters into the soil surface. Percolation refers to downward movement of water through soil and rock layers. Subsurface flow transports or travels groundwater through geological formations. Understanding this hidden cycle is essential for watershed and groundwater management for the civil engineering and construction point of view. Also, geological subsurface exploration also plays the important role for to study the hidden water cycle which is available beneath to the earth's surface. The groundwater, or we can say that defining the groundwater, that is the liquid water residing entirely within the interconnected voids, fractures and pore spaces of the earth's outer shell. That is the groundwater, which is the water stored within the interconnected pores and fractures below to the ground. It occupies void spaces in rocks, sediments and soils. Groundwater influences the engineering properties of soil and rock masses. Pore water pressure significantly affects slope stability and foundation performance, where hydrology and hydrogeology conditions must be considered during infrastructure planning and design of foundation purpose. So the engineering reality and the structural impact, which is most important, depends on the groundwater and its condition. The engineering reality, where the outer shell of the earth consists of predominantly of solids, but gases and liquids are also present. While considering the construction activity point of view, we can focus the conditions of subsurface and surface also. What is the structural impact? That gases and liquids are structurally critical because their presence in pore spaces modifies the physical properties of solid rock. Here, zones of subsurface water. Three zones are there: zone of aeration, then water table, and zone of saturation. So, zone of aeration is also known as Wadham zone. Zone of saturation is also called as a phreatic zone. So, the Wadham zone or zone of aeration, where water is held by capillary action, where pressure is less than atmospheric pressure. And in zone of saturation, that is the phreatic zone, where all interconnected voids are fully saturated, and this is the true groundwater or availability of groundwater. In between the zone of aeration and zone of saturation, the exact water table is present. So the subsurface water is divided into two zones: zone of aeration and zone of saturation, as explained in the picture. The zone of aeration contains both air and water within pore spaces. Water in zone of aeration is the zone which held mainly by capillary pores or forces acting by the capillaries. The zone of saturation contains completely water filled pores. The boundary separating these two zones is called as a water table. What is meant by dynamic boundary? So here the pressure boundary and the surface intersection, two phenomenon are important with reference to the topographical conditions of hilly region and flat terrain, along with the subsurface geological exploration. The surface interaction is that where the water table breaches the surface elevation, as shown in the picture. A visible body of water, that is spring, river, lake, is formed with reference to its high flood level. The whole pressure boundary line is marked on the both side of that banks. That is not a flat underground lake, a dynamic surface where fluid pressure equals atmospheric pressure and roughly mirroring the land's topography. That is the actual dynamic boundary marking. So that the water table is not a flat underground water body. It is a dynamic surface where groundwater pressure equals atmospheric pressure. The water table generally follows the shape of surface of topography, as shown in the picture. Springs, rivers and lakes form where the water table intersects the ground surface. Water table fluctuations indicate changes in recharge and groundwater extraction. So that water which is available with reference to the pores, with reference to the capillary fall or rise, or any perch aquifer, that whole water which is a part of that dynamic boundary. Now the aquifer structural synthesis, most important descriptive part, where the upper geological boundary, pressure state, recharge zone and vulnerability are the legends. On the basis of that, we can study the structural synthesis of aquifers. There are three types of aquifers: confined aquifer, unconfined aquifer and perch aquifer. So for unconfined aquifer, upper geological boundary, the water table, pressure state is the atmospheric, recharge zone will be the direct above to that unconfined aquifer, but vulnerability, high risk of surface contamination, that is open lock icon. Means the aquifers are geological formations capable of storing and transmitting groundwater. Unconfined aquifers are directly connected to the atmosphere through permeable materials, while confined aquifers are bonded by impermeable layers known as aquicludes. So confined aquifer, upper geological boundary is aquiclude, that is impermeable rock, where pressure state is hydrostatic and the recharge zone will be the distinct outcrops. But the vulnerability for confined aquifer is geologically protected, that is closed vault icon. Then recharge condition differ between confined and unconfined aquifers continuously, so that aquifer characteristics determine groundwater availability and the quality of groundwater. So the perch aquifer point of view, we study the impermeable lens which is the upper geological boundary, and perch aquifers are smaller scale or smaller size, having the atmospheric pressure state where the recharge zone is directly above to that level. So the vulnerability is prone to rapid depletion, means perch aquifers are not available continuously. They are for 1 or 2 months only after the rainfall below to that earth surface. Moving towards the unconfined system, the diagram itself suggests that the open boundary and the local responsiveness, where open boundary, an aquifer whose upper boundary is open to the atmosphere through permeable rock or soil, that is open boundary, where the local responsiveness is that highly responsive to local rainfall and drought, but highly susceptible to surface spills. Water in a drill well stands exactly at the level of the surrounding water table. So the unconfined system, or we can say the unconfined aquifer, has no impermeable layer above it. Its upper surface corresponds directly to the water table. Groundwater levels respond rapidly to rainfall and drought conditions. These aquifers are easily recharged but highly vulnerable to contamination. So the most shallow wells obtain water from unconfined aquifers. With a confined system, which is dependent on the impermeable trap and the hydrostatic pressure, the impermeable trap, where groundwater trap between impermeable soil strata, along with hydrostatic pressure, where aquifer aquicludes are studied, that an undirected all-sided pressure which is acting on it, because it is enclosed and fed with from a higher elevation, the water is under immense pressure. So the pressure water is connected with reference to the confined system, where the hydrostatic pressure scale is important to study or to measure the pressure. So the confined aquifer is trapped between impermeable geological layers. Groundwater remains under hydrostatic pressure, where recharge often occurs at distinct outcrop locations. Water levels in wells may rise above the aquifer due to pressure conditions, and the confined aquifers generally provide cleaner and more protected groundwater resources. Perch system, which is the smallest part or smallest zone of saturation of trapped water high above to the main regional water table, which is a localized saturation. The structural cause for that perch system is formed when a small impermeable rock layer like clay sands or dense shell, which intercepts downward percolating water. Where engineering point of view, there will be engineering risk which is often misleading during drilling, provides a false reading of the actual water table depth, and yields unreliable, quickly depleted water supplies, and that quantity of water is too small with reference to the perch system. Fundamentals of aquifer and its properties. There are the most important properties for aquifer are porosity and permeability. Porosity measures the percentage of void space in a rock or soil. Permeability measures the ability of water to flow through these voids present. So high porosity does not always imply high permeability. Both properties control groundwater storage and movement. So civil engineering projects rely or depend on these parameters for seepage and foundation analysis. So the porosity, which is the capacity, and the permeability, which is the flow. So the percentage of rock's total volume that consists of void space, which is the porosity, which determine exactly how much water the structural container can hold. Secondly, the ability of a rock to transmit fluid, that is the permeability, which show the flow. High porosity does not guarantee flow if the pores are not interconnected, that is the clay portion. Groundwater movement, or we can say that the groundwater flow mechanism of water, the two concepts are there: hydraulic gradient and the faults as conduits. So what is meant by faults as conduits? Fault planes act as a vertical superhighways for fluid discharge. Springs align along the foot of a mountain range indicate a fracture permitting deep penetration of circulating waters, as shown in the image. That is the hydraulic gradient second part, where groundwater always moves from areas of high hydraulic head, that is pressure plus elevation, to low hydraulic head. So the groundwater flows from higher hydraulic head to lower hydraulic head, where flow occurs through interconnected pores and fractures. That hydraulic gradients determine flow direction and velocity, which depends on the geological structures, are strongly influence groundwater pathways. So understanding the groundwater flow is essential for dewatering and seepage control. What is the importance of hydrogeology in civil engineering? With reference to the geological subsurface exploration point of view, each and every soil layer, rock layer, there are n number of lithostatic pressure is acting. There are so many pores are available with reference to the fold plane and fault plane. So the groundwater conditions influence foundation design and construction safety. So hydrogeological studies are required for dam, tunnels and reservoirs. Groundwater pressure affects slope stability and retaining structures. So water resources planning of that construction activities which are depends on an aquifer and its evaluation criteria. So hydrogeology supports sustainable infrastructure development based on the engineering challenges and underground openings. So what are the engineering challenges? Excavating structural rock means managing the fluid inside it. High fluid pressure in the pore spaces of rocks which are partially balances the lithostatic pressure, that is the massive weight of overlying rock. Secondly, underground openings, that is removing water during excavation removes critical structural support. Calculating the exact ratio of pore pressure to lithostatic pressure is required to prevent tunnel collapse. Anthropogenic groundwater problems. So three basic problems are listed: drawdown, subsidence and contamination. Drawdown means over extraction creates a localized zone of depression, reversing natural flow vectors and drying up adjacent wells. When we excessively extract the water from groundwater, then that drawdown of or the depletion of water table will be seen. Secondly, subsidence. Without pore pressure to balance lithostatic weight, the solid rock matrix collapses and the land surface permanently sinks. That is settlement, or we can say that the desettlement of the stable rock surface and strata. And third one will be the contamination, that is pollutants follow the specific permeability pathways of the host rock, making plumb tracking a complex structural puzzle. That means the whole underground water or groundwater table may get contaminated due to that pollutants which are flowing through that porous material or permeability action. So the summary for the hydrogeology concept, which is depends on the hydrogeologist use boreholes, wells and pumping tests to study aquifers. Geophysical methods such as extraction through the bore wells or tube wells help identify subsurface water bearing formations. Remote sensing helps in mapping groundwater recharge zones. Also, we can use the GIS for special data sets for groundwater assessment. These techniques of remote sensing and GIS with reference to some models improve groundwater exploration and management. Groundwater will stored within pores and fractures below to the earth's surface as shown in the picture. The water table separates unsaturated and saturated zones. Aquifers acts as natural resources for groundwater storage and transmission. So groundwater flow depends on geological conditions and hydraulic gradient. Hydrogeology plays a critical role in modern civil engineering projects. So hydrogeology is the structural, pressure dictates flow and engineering requires balance. So three basic components which are more important to study the hydrogeology and its whole phenomenon. Stay tuned guys, happy learning.